Hey everyone, I'm Sakshi, and today we will be discussing design patterns in distributed systems. So, what are distributed systems? Well, according to Ryan Thelen, it is a collection of independent computing nodes interconnected via a network collaborating on a task. Distributed systems are used to address the challenges of scale, availability, and data processing in modern software engineering. They provide the foundation for many of the applications and services we rely on in our digital world. We've all come across distributed systems, wherein the network of computing nodes split up a particular task to coordinate their efforts to complete a job or task more efficiently than if a lone device were to do it. This concept of divide and conquer has been used in many applications as well as frameworks, especially the ones that deal with large amounts of data. Here as seen are a few examples of the same. Databases such as Cassandra HBase, message brokers as Kafka Pulsar, infrastructure as Kubernetes and Zookeeper, and file systems like HDFS and Ceph. Historically, distributed computing was expensive, but thanks to software as a service, these offers have expanded functionality. It has become available to large and small businesses today. Before we dive in, does anyone know what design patterns in a distributed system are? Let me follow that up with another question. Do you know why we would need such patterns? Let's take a look at these questions, shall we? Ryan Thelen says that distributed design patterns outline a software architecture for how different nodes communicate with each other, which nodes handle each task, and the process flow for different tasks. What this essentially means is that looking at the problem space, finding a pattern that could be seen in multiple similar scenarios, and then designing a generic piece of software that works for this entire problem space is what design patterns are. Developers do not have to solve an already solved problem from scratch, but instead they have to use a relevant pattern, thus saving a lot of time and effort. Let us look at the broad categorization of these patterns. Object communication. It is a distributed system which comprises nodes that frequently communicate with each other. This type of design pattern covers messaging protocols and permissions for different components of the system to communicate with each other. Security. It handles confidentiality, integrity, and availability concerns to ensure that the system is secure from unauthorized access. And finally, event-driven. The patterns that describe the production, detection, consumption, and response to system events are well within the range of these. Command and query responsibility segregation, or CQRS. In traditional architectures, the same data model is used to query and update a database. That's simple and works well for basic operations, but what about those which are more complex? These are mostly used in data-intensive applications and microservices. However, this approach can become unwieldy in more complex applications. Read and write workloads are often asymmetrical with very different performance and scale requirements. The CQRS pattern focuses on separating a distributed system's read and write operations to increase scalability and security. This model uses commands to write data, to persist in storage, and queries to locate and fetch the data. This is a synchronous system, and all operations are handled by a command center, which receives user requests. The command center then fetches the data, makes any necessary modifications, saves the data, and then notifies the read service. The read service then updates the read model to show the change to the user. With use cases similar if not same as CQRS, 2PC, or two-phase commit, will sound a whole lot familiar to you guys. Many of you have worked on microservices-based backends. They're a specific type of distributed system that consists of multiple different services performing different tasks. For example, in an online shopping scenario, 2 different services handle the wish list and cart. They must communicate when you want to add something from your wish list to your cart. If a user requests to add something from the wish list to the cart, both services would be involved. Every global user transaction involves smaller local transactions by every service at the back end. Does anyone see a problem here? Let me explain. What would happen if one service's local transaction fails? Do all the services roll back on their transactions? What happens to the global transaction? How are concurrent transactions handled? 2PC handles all of these problems in 2 phases. The prepare phase, in which the central control tells the services to prepare the data, and the commit phase, which signals the service to end the prepared data. All services in a 2PC system are locked by default. Meaning that they cannot send data. While locked, services complete the prepare stage, so they're ready with the data. The coordinator then unlocks the services one by one and requests its data. Once all the prepared data has been sent, all services unlock to await new tasks from the coordinator. Simple, right? This handles contention management for concurrent requests, and it is also a lot more consistent than CQRS. Now, both patterns that we saw were synchronous, meaning they had a central command telling services what to do next. This one's a little bit different. It's an asynchronous design pattern in which all the communication is entirely between different services. Let's have a look at Saga, shall we? Let me explain. Here, we're trying to solve the same problem as the last design patterns, but in an asynchronous fashion. As we'll see, this overcomes some of the disadvantages of the previously covered synchronous patterns. Saga uses Event Bus to allow services to communicate with each other in a microservice system. What does this mean? It means that the bus sends and receives requests between services. We have a sender service and we have a receiver service. The sender service sends an event on the event bus, and the listening service listens for these events. When the listening service receives an event, that is, its trigger to start performing its operation, and once it is done, it will notify the service that is supposed to send this output to. But if that service fails to complete the action, that local transaction is rolled back, and the event is sent to the next listening service. You must be thinking, how is this different and why is Saga better? Saga removes the central control element to manage the flow better and reduce the required back and forth communication, thus making it a lot more efficient than what we just saw. The patterns that we discussed up till now are the most common ones used by programmers in tackling problems faced in distributed systems. Once we understand these, we can move on to some intermediate and advanced patterns. Here I've listed some more for further reading. They're good pointers to dive deeper into designing and implementing distributed systems. As we wrap up, you can see that I've listed some references that I've used to understand design patterns and distributed systems and make this presentation. But this presentation reflects a very small part of what is contained in these articles. If you are interested at all, I highly recommend that you read each of these and more. That's all for today, folks. Thank you so much for watching, and I hope you enjoyed learning.